Mainly MDP is used for institutional learning, and last year it was covered as part of the AI course. Okay. But it is directly related to us. And MDP actually is an extension of two things. One is dynamic programming. All of you are very well aware about that. Another one is Markov reward process. We already covered Markov reward process. Where in this condition, a reward is given. So, a combination of these two actually makes Markov process. So, dynamic programming is already algorithm process. Actually, there is a course there is the states of condition. The agent actually takes some decision. Based on this decision, sometimes we call it an action. Based on this action, what happens? The next step of the chain or Markov chain is set. And the action also decide the amount of reward that will be. So, action taken by the agent, takes action. This action decides two things. One is the next step and the reward. And actually, by this way, our objective is to maximize, select the action so that the reward is maximized. So, ultimate objective of the Markov decision process is to select the set of actions that will call policy. Finding the policy that will maximize the reward. Is this clear? So, all of these things are known. Let me start again. And MDP is an extension of DP, dynamic programming, and MRP is Markov reward process. We discussed Markov reward process. Where this is the rest of the condition, a reward is given. So, if you are in condition, there is a condition, you will have a reward, or you can consider an expected reward is given. And in an MDP, we have an asset that agent actually takes decision. At this stage, before taking the transition, actually, the agent takes an action. This action actually decides two things. What will be the next step of the process and what will be the reward of the process. Now, if you are in a state and you decide that this will be your action, then the action will decide what will be your next step. That means, in case of a Markov chain, what happens? We have to provide from I to J. Now, how the action is affecting the transition? Say if you have two different actions, then for actions one, there will be one transition providing an action. And for two, you will have a different transition providing an action. That's how an action is affecting the next step. Since whatever you are taking second actions, then the probability is different, so you will be ending in a different step, unlike the other one. Similarly, in a Markov reward process, what we have only a reward matrix. Reward matrix is something like this. See, if you consider a two-step Markov chain, then it is the reward matrix. We will have reward R1. If there is a transition from step 1 to 1, then the amount of reward that process will be R1, then R1, R21, R2. Now, when we have a designated place and the agent actually takes actions, R1, R1. Right. Now, whenever action 1 is taken, this will be the label. When action 2 is taken, this one will be the label. That's why, in case of an MVP, an exit actually decide the next action to be taken, and based on the action taken by the agent, next state of the process, given and accordingly reward that is given also determined by the action taken by. So this is the very basic of it. Let us step by step we'll go from DP. We'll see an example just to remind you. We'll see an markup reward process and finally we will go for the game. Now, solving an MDP actually has three different one we call it value iteration. Another one we call holistic iteration. And the third one is the linear program. Linear programming actually is not a programming, it's a mathematical tool to solve linear optimization problem initially used by the makers. And they use it for scheduling, but we will not cover this one. Our actually focus will primarily be on these two, value iteration and value iteration. Hopefully we will try to cover the value iteration and value iteration by the policy iteration. Also, an extension of Markov decision process is semi-Markov decision process. If you can recall, a Markov process can have a semi-Markov process. Can you tell what is semi-Markov process? Down by real condition. So, what is semi-Markov process?
Holding time is not
Holding time is this is a very different. So, we in a Markov chain, the amount of time that process stays in a state should have to be memory required. For a continuous term Markov chain that defines that the time will be exponentially distributed. For a discrete term Markov chain, eventually this will have a generalized distribution other than the memory distribution. Then actually the Markov chain is semi-Markov chain and it has we will discuss this one with forward, right? Now, the Markov precision process that we are covering here is the pure the underlying Markov chain is a pure Markov chain. So, in case of a discrete time Markov chain, it will be geometrically distributed or exponentially for one reason. Maybe we will be covering the discrete time Markov precision process. So, you will find that there is a section semi-Markov precision. Even an extension of this one also available. This one is partially observed Markov precision process. Right? Partially observed is like the Indian Markov model, where actually the underlying Markov chain is not observed at all. That we have seen in the last 3 or 4 classes. So we will not cover this one. We do not cover, we will cover. I think we will not cover, or we will just see what is there. So this is the summary of this chapter. Mainly our objective will be here, Markov precision process, and that I did not mention is it is the main building block of reinforcement learning. I know you don't know whether it will be covered in the AI courses or not. Since machine learning did not cover it, I think AI will cover it. You can explore it. So my job this year is to introduce the macro precision process that actually is the building block or fundamental math behind this reinforcement learning. So I already mentioned an agent takes sequence of decisions, and this our objective is to find the sequence of decision so that he maximizes the take decisions so that the reward is maximized. Now, in between these two things, what we have decision actually is it observe the system at a specific point of time we call decision report and gather information to take the decision. So what happened in the past he gathers and this actually associated with we call it a reward. The reward can be positive or so we have an asset that takes decisions and our job is to identify the decisions that maximize the reward. We call such a decision. Sequence of decision is policy, and we want to select a policy that will maximize our reward. So this is very simple thing. Everyone does this. Whatever we do, we maximize our reward. Whenever, say, Islamic course has a easier path to get a plus, many students sacrifices math. Because if you invest on Islamic, then you will get a plus, your CGPA will be actually right? Now, even if there is a problem, there is a very good thing, we call it discount. Discounting or discount factor. What is discount factor? Very interesting. Say, now you are investing more on Islamic course in the first semester. Your GPA will be high. What happens? There are subsequent courses in second, third, and fourth semester which requires the knowledge of math. That actually will affect your eventual grades for those courses, and eventually what will happen? Your reward will be. Is this clear? Actually, in terms of MDB, we are saying that it's the knowledge of math will affect. In MDB, actually, a discount factor is that since it's a multi-stage decision process, what we mean by the term multi-stage decision process? There will be multiple stages. In each stage, the agent has to take decisions, and based on these decisions, our rewards actually are different. So, say 2, 3, 4, or 5 stages are there, and decisions are taken in all stages. Now, if we can focus on an immediate reward, or you can consider future reward. Now, the problem is, due to the devaluation of money, $1 that we have today or in the future, that actually does not have the same value after some time or now. That's why a discounting factor is added, we call it beta. And so, future actually rewards are less. So, in that case, we can be more focused on the current one, or if the scenario is different, then we can be more focusing on the future. So, as I was mentioning, whether you will go for the Islamic or the math. From a first year student's perspective, the same energy in Islamic will give you guaranteed class. But the same time and effort in math will not give you a class. So what to put more effort on Islamia and a class is given, less effort is there, say a B grade is there, but this B grade eventually will affect your future grades. Anyway, this is what is the discounting factor. We will be discussing the discounting factor later. Now, in an MDB, there will be components, as there will be a markup chain. So, a state circle. Set of state actually is represented by the character S. And agent will be there. The agent will take actions. We will have a set of action. And this set will be finite. Then there will be, for the Markov chain, since there are states, we will have a transition probability matrix. This one, or we can consider P is the transition probability matrix, where actually each element of the matrix represents the probability of transition from state I to state J. Then this actually transition probability depends on the actions taken by the agent. So the action comes first. The action decides what will be your transition probability, and also the action decides what will be your reward. So if we consider this one, if you are currently in state I, and agent actually takes the decision action A, then based on this action, you will have a different probability of transition from state I to state J, and when there is a transition from I to J, a reward based on once again action, you will have a reward. So, if we say in single term, there will be a set of actions available in the agents 1, 2, 3, 4, whatever, and for each actions, you will have a different matrix for transition from state I to state J, or transition probability matrix for each action. Similarly, for each action, there will be matrix for the reward. So, one thing that we actually need to remember from here, since MDB is associated with an agent and a set of actions, based on these actions, we will have a set of probability transition matrix and the reward matrix. For example, if you consider the set of actions are D1, D2, and D3, then we will have a transition probability matrix D1, probability transition matrix D2, probability transition matrix D3, and also we will have a reward matrix for the actions D1, reward matrix for the actions D2, and reward matrix for the actions D3. So the task will be carried out. Expected. And there will be a discount factor. A value between 0 and 1 will define the discount factor and representing the importance of the future rewards as compared to the immediate rewards. Okay. So impact of the future reward and the current reward will be evaluated, compared, and in case of beta will be defined. For example, beta 1.9. And in each actually stage, the beta will be multiplied. We will see. As we mentioned, there will be decision epochs or decision actually period. And these decision periods are defined by the P can be a discrete set, P can be a multiple set. So, what is we will be considering a discrete time entity, and when P is finite, we will call it a finite horizon entity. If P is infinite, then we will call it infinite horizon entity. So, discrete time, as you already know, time is divided into interval of equal length, and each interval an action is chosen. Based on this action, a rendition occurs and a reward is given. On the other hand, in case of continuous time, after a continuous amount of time, an action will be taken and then a transition will be there. And also, you can consider that an event is associated with that. When an event will occur, an action will be taken, a transition will occur, and a reward will be given. Since we will be focusing on here the discrete time, forget this one for now. So our goal will be a discrete time MPP, and in case of the discrete time MPP, we have two options. When t is infinite, like this, or t is finite. When t is finite, we call it a finite horizon, and when t is infinite, we call it an infinite horizon. So, a policy actually is a set of decisions, a rule for making decisions. In the decision process, you take these decisions, D1, D2, Dn minus 1, when you actually, there are 8 stages, we call this T as the policy. And our objective is to find the optimum policy which leads to maximum reward. So eventually it is a method of solving some sort of optimization problem. Okay, a policy can be stationary. This is important. Since we will be considering a stationary policy. What is a stationary policy? A stationary policy actually is time independent. For example, whenever the process will be in state I, always the same action will be taken. And I to j, it will move with the same probability, and the reward will be same reward will be given. It does not matter whether it is morning or it is evening, it is time to say here, time this is T1, time this is T2. If the process is currently in state I, here and here, in both cases, the same action will be taken. Since the same action will be taken, the probability of the emission will be same. With the same probability, process will move from I to J, Vij will be same. And the reward that will be given Rij, it will also be same. That means it is homogeneous. So we are considering an MPP which is homogeneous. So the policies are stationary. It does not depend on time. When if it is not homogeneous, then actually besides now consider to be Ij is depending on the action, we will look at time parameter. So at what time you are doing this one. So both the time and the action will define the probability of rendition, but in case of the stationary policy or the homogeneous case, we do not consider this one. We Ij will only depend on the actions taken by the there are huge or many applications of MPPs. I do not need to actually mention this one. One is robotics. Actually, the movement of the robot, whether it will go to the right, left, forward, backward, and actually the movement may be facing some obstacles. Based on the obstacles, actually, what is it? For example, you are forwarding a move of robot towards this wall. So eventually it will produce a negative reward because you need to come back to go to the desired destination. Operation research. You know what is operation research? Operation research? Actually, operation research actually is a discipline in both advanced mathematics and numerics. But actually, optimization so different, for example, these traveling systems or then the other types of optimizations with different types of scheduling, different types of say this multinational companies actually the delivery man, travel staffing assessment problems, all sorts of things actually in this discipline will be optimization process of different
I'm on.
operations. And some of its names are operations, no resources there actually. In APP you can use economics and finance they use, and one is not mentioned is here actually. Reinforcement learning actually we use. As I already mentioned, there are three different types of solutions: value iteration, policy iteration. In value iteration, what we do, we have an iterative algorithm that upgrades the value of each step until the algorithm converges. Or actually, for the last step and for all policies, we will today see the value iteration method. And the policy iteration method actually, it alternates between policies. And when it finds two policies generating the same result, it considers that it has become alternate. Linear programming, I think you are familiar with linear programming, right? And it goes to linear programming. Linear programming actually is a method of solving optimization problem where the functions, all the functions are linear. And one of the best methods for solving linear programming is actually it was discovered during the Second World War. I forget the name. Very well known. Sorry, I forgot. So linear programming actually is a branch of once again advanced mathematics. That was very specific where optimization of linear problems are actually solved. Now we will actually see an example of the. You are very familiar with DB, so I do not know DB. Because I do not, actually I have not developed algorithm for a long time. What we need to do here is just how this actually, as I mentioned that this MPP is an extension of both DB and Markov reward process. The solution of MPP actually is related to this dynamic programming and this Markov reward process. So we'll see, following the text, we will see the example, but we will not go into the details. How the problem actually is defined. You have a resource, X units. You have a set of activities, N projects, or N activities. Now you need to invest this resource X into N projects so that you can maximize your profit. How? Then investing 1 unit to the first project has a reward. Investing 2 units to the first project has a reward. So you can invest all X units to the first project, there are rewards. If you invest all the X units of resources to the second project, there are rewards. Third projects, N project, then there are rewards. Now question is, what is the amount that you will invest on project 1, amount that you will invest in project 2, that you will invest in project 3 and project 10, and that eventually gives you the total reward. Now, if we define RIXI is the reward when you actually invested on project I and the This xi is the amount of resource.
সকল আসতো কাকাকালে শিখলাম বলছো
Then r1 xi is the
বলছো
reward that you get from project.
ক্যারেক্টারদের না বলা রিয়েল না
Different project you will have a different. So if we consider there are only 3 projects, that means n equal to 3, then R1 X1 is the reward that you will get from project 1 by investing X1. R2 X2 will be the reward that you will get from project 2 by investing an amount X2, and finally R3 X3 will be the reward that you get from project 3 if you invest X3. Let's say this is the total reward. Then our objective is to maximize this. We want to maximize Z. Z is the product. Now, you cannot actually invest more resources than you have, or you cannot invest less resources than you have. If you invest less resources, then the resources will be unused. If you invest more resources, actually then you have some negative things. The things that you do not have, you are already invested. That's why all optimization problems comes with a set of constraints. What is a constraint? A constraint actually is a condition that the optimization problem must have to satisfy. So here the constraint is that x1 plus x2 plus x3 should be exactly equal to x. Usually the constraints are written with the word subject. So this is the standard process of mentioning an optimization problem, that we need to maximize this one. We call it the what do you call it? We call it objective function. So for every optimization problem, there will be a function, we call it objective function, and our goal will be either to maximize the objective function or to minimize the objective. And optimization problems are either constrained or unconstrained. In case of a constrained optimization problem, you need to mention that with the word subject. Here the constraint is the allocated resource should be equal to x. It cannot be greater than x, it cannot be less than x. Actually, this equal sign here in the constraint makes the problem more difficult. Usually we prefer this one. Allocated resources should be less than or equal to x. And usually we call this functional constraint. And this one is also a constraint, but this one is not a functional constraint, it is a non-negativity constraint. Non-negativity constraint because the allocated resource cannot be negative. So this is our objective, the optimization problem, and using TP we will solve it. Here is the problem. We assume that there are 3 projects, there are 3 activities. On these 3 activities, we will be allocating a total resource of 6 units. In the first activity, x1, if we allocate the resources 0, then the reward is 0. If we allocate 1, the reward is 3. If we allocate 2, reward is 6. Actually, it is multiple of 3. Here, there is a jump. Allocating 4 resources will result in a reward of 12, 5 resources will result in a reward of 64, and allocating 6 resources, there will be no added value. Now for x2 is this one, for x3 is this one. There is a typo here. Just by seeing this one, a human being can easily see what should be your optimal reward and where should you invest. In project 1, how much, in project 2, how much, and in project 3, how much. Can you see what should be the optimal reward? A human being actually is very fast. Multiprocessing is there, but a computer actually, it will compare, okay, if I allocate 0 here, 0 here, and 6 here, then what will be the reward? Say 6 here, 0 here, and 0 here. What will be 16? So it will find all combinations, but a human being can easily see. You can see what is the optimal reward here? What? 16 is the largest number, right? So you should be allocating 16. You can easily see 16 is the largest number. Second thing is how much actually resource do we have? 6. And already we invested how much? 5. So 1 is remaining. Either you can allocate it here or you can allocate it. If you allocate the remaining 1 unit in project 2, then the reward will be 2. And if you allocate into project 3, it will be 1. So the total will be 16 plus 8. So the optimum actually reward that we can find from here is 18. And if we want to get this one, then we need to invest 5 units here and 1 unit. DP actually will step by step will find it. So if we use DP here, then I don't know what will be the math. There is one in the book. I will follow that one. But can anyone check what will be the algorithm of finding that the optimal reward that you can find from this problem is 18? Anybody? Anyone competitive programming? Okay. The algorithm actually follows exactly this. What it does, what it does actually, it actually first find out the optimal return that it will find from the end instance. To do so, what it does, it defines what is that variable? It defines a variable, I repeat this one? Okay. It defines a variable p and x. What does it mean? It means that if you are currently in the nth activity, how many activities are there? This is the first activities, this is the second activities, and this is the third activities. If you are in the nth activities, and if you invest x resources, then these x resources will be actually, this should be not n, this should be k, following this one. So if you are currently in the kth activities, and you are actually investing x resources, not all in the kth activities, rather k through n, then what will be your maximum reward? It's the one here. For example, if we write here 3 to 5, not 5, okay, 5. 3 to 5 indicates if you are in the second activities and you will invest 5 unit of resources in activity 2 and activity 3. So here there is equal. So 2 and 3. Then what will be your maximum reward? Then we can see. How can we calculate? We will be using 5 units of resources. 1 will be, okay. There will be 0 in activity 2. Then we need to use how many in activity 3? 5. 1 in activity 2, then 4 in activity 3. 2 in activity 2 and 3. So total 5. 3, 2, 4, 1, 5, 0. So there are 6 options. Why is 6 options? What will be your maximum reward? When 0 and 5 is there, 0 is there, and 5 is here, this is 5 and is typed in the book, then your total reward will be 12. Now, if 1 is here and 4 is here, then it will be 2 plus 8 equals to what?
Okay.
Sorry, not 9, 10. Then 2 is here and 3 is here. It will be 4 and 5 equal to 9. 3 is here, 2 is here. 3 is 6, 2 is 3. Then it is 9. 4 is here, 9, 1 is here, 1. Then it will be 10. Finally, 5 is here, 0 is here. This will be. So, for this variable, d to 5, the optimum resource, optimum reward will be what? Optimum reward will be. By this way, actually, it calculates first for the nth state, then or the n project, then n minus 1 project, then the first project. When we actually come to the first project, then all resources must have to be exhausted, and then it finds the optimum value. Okay? So what happens? The algorithm actually has the variable is p ax.
So more
It is defined by the math. If you can consider what is this one? It is the maximization of what? The reward of allocating xk amount in the kth state and remaining amount in the remaining how many? From k to n. Let's say k minus n, 1 minus k steps. But here, since we have 3, that's why the amount 5 was allocated in 2 and 3. If we were come to 1, then out of 5, if we were allocated 0 here, then 5 will be allocated to 2 and 3. That's why we have a actually recursive function that maximizes, and this recursive function here will have, what will be the value of xk? Xk will have the value in between 0 to x, and this x will have the value 0 to x to x. Then actually this maximization is done for the values 0 to x allocated here, and the remaining values from the remaining step in 1n minus 1 steps, and just a minute. This is k plus 1, yes, not n minus 1. So, sorry, this is not n minus 1 step, this is k plus 1. That means when we are in the k step, we are in the 2, then this value represents the total reward that we get from the remaining steps if we allocate the x minus k amount of resources. This is the total k x resources that we want to maximize here. X minus k is the remaining. So by this way, actually, we can optimize the total reward. Let's see the steps first. Then this equation is here, following the text, and we have the initial state. The initial state, what it does, it actually, for the value of this one, when k is equal to n, it actually allocate these rewards to the n state. And accordingly, what we will have is V3 0 will be 0, V3 1 will be 1, V3 3 will be 3. Just it is the reward that we get from R3X. And once we have this one, our objective is to find out V2X. And what will be the possible values of X? We'll see only one step. This one. X will be from 0 to X, and this V2X will be maximize this one for the value of xk in between 0 to X. And here we will have R2xk plus k plus 1 x minus xk. Which if this is the case, then we need to first select the value of x. What should be the value of x? From this sense. So we need to calculate first V2 If we have V2 0, then the maximization will be what? Since we have 0 resources to be allocated, so we need to allocate 0 here, and we need to calculate Vk plus 1, x minus 0, 0 minus 0 equals to 0. Now, what is k plus 1? If it is 2, k plus 1 is 3. Then, and since this is a single value, what will be the resource here? R2 0 is 0, and V3 0 is 0. So it will be 0 plus 0 equals to 0. Actually, 0 does not require anything. Now, V2 1, this is the first important one. We need to find out the maximum of xk equal to 0 to 1. Then the function starts here. R2 xk plus V3 x minus x. So please focus here. If you understand this process, then the whole algorithm will be very simple. Now we need to start with the value of x equal to what? 0. And we will go up to 1. When x2 is equal to 0, then the maximum will be between what? This one is 0 and this one is x is what? 1. Xk is what? 0. 1 minus 0 is? Let me write it. Here it will be R2 0 plus V3 1, and another one is when xk is equal to 1, it will be R2 1 plus V3. So we are getting this. How we get this one? So when this one is xk is equal to 1, then we will have the range of xk from 0 to, this is x. Sorry. When this one will be xk will be from 0 to 1, and sequentially we need to allocate the values of xk here first 0, this one, then xk is equal to 1. If we have this one equal to 2, let me see it here, just V2, then what will be the maximum function? The maximization function will be R2 0 plus V3 what? R2 1 plus V3 R2 2 plus V3 Can we compare these two functions? Here the limit of xk is from 0 to what? x. If x is 1, then it goes in between what? 0 and 1. If x is 2, then it goes between what? 0, 1 and 2. If x is 3, then it goes from 0, 1, 2, 3. And then this maximization, since it is ranges from 0 to 1 for xk, then we have 0 here, 1 here. Since this is the difference between x and xk, when x is 1 and xk is 0, then this difference is 1. When xk is 1, then difference is 0. Now here, when x is 2, xk is 0, then b3, what will be here? 0, 1, 2, 3. It will be, what is the variable here? X minus xk. What is the value of x? This one, 2. What is the value of xk? 0. Difference is? Now here xk is equal to 1. Then this one will be what? 2 minus 1 equal to? This one is 2. Then this one will be? And if we come here now, then we can find this next. R20 is what? R20 is the reward where we get from activity 2 if 0 resources allocated. From the table it is 0. If 1 resource is allocated, it is 2. If 2 resources allocated, it is 4. Then we can find out here. This is 0. This is 2. And when 0 is allocated here, 1 is remaining for this one, P3, 1 is 1. This one is 0. So what is the maximum value? This is 2 plus 0, this is 0 plus 1. This is 1, this is 2. The maximum value is 2. If we come here, then we can write the max is R20 is what? 0. D3, 2 is 3. R21 is 2. D31 is 1. R22 is 4. D30 is 0. So, what does it mean? It means that if we allocate 2 units of resources in activity 2 and 3, 2 units of resources in activity 2 and 3, then we have 3 options. How? We have 0 resources in activity 2, 2 resources in activity 3. And the reward is 0 resources from activity 2, and 2 resources in activity 3, just from here to this 3. So total is 3. And also what we can have? 1 resources in activity, 1 resource in activity 2, sorry, and 1 resources in activity 3. Total reward is 2 plus 1. On the other hand, final one, 2 resources in activity 2 and 0 resources in activity 3. Total reward is 4. So this one is maximizing the reward. If we allocated 2 resources in activity 2, then this is maximizing our. So from here, now if we look at here, then actually what does this dynamic program is doing? When we have actually say from here we want to allocate say 2 resources, then we have 2 options. One is 0 here and 2 here. Okay, let me change the color. 0 here, 2 here. 1 here, 1 here. 2 here, 0 here. Now what will be the reward? If 0 here and 2 here, the reward will be 0 and 3. The reward will be 3. 1 here, 1 here, the reward will be 2 and 2, 1, 3. And 2 here, 4 and 0 here, the reward will be 4. So by this way, for each amount of resources from 0, 1, 2 up to 6, we need to find out if all 6 amount of resources are allocated step 2 and step 3, what will be our maximum reward. And at the same time, we need to remember one variable. We define this variable as MKX. This MKX actually represents the amount of resources that we use here that maximizes that reward. For example, here, if we use 0 resources, the reward is 3. If we use 1 resources, the reward is 3. And if we use 2 resources, the reward is 4. So for this one, MKX has the value 2. That means M22 has the value. This one actually is there to keep track of this value. Now, if you have any question, we can discuss. Otherwise, this is from the text. I can just show. We have seen this one. And we have seen this one. No, we have seen the last one. We have seen this one. This one, B21 actually is giving us the amount 2, and B22 is giving us the amount 4. And when we are considering this, B22 is maximum reward is 4. Actually, the 4 is coming from this one, and this one actually has the value of x is equal to 2. That's why M is equal to 2. If you similarly see this one, what we want to do, we want to find out the maximum reward from step 2. When we are considering step 2, actually B2 is not only considered step 2, but also all the subsequent steps that since it is going backward. So if 6 units of resources are used, then we can use 0 unit in step 2, 1 unit in step 2, 2 unit in step 2, 3 unit in step 2, 4 unit in step 2, 5 in 2, and 6 in 2. When we use 0 in step 2, then B3 we have 6, here it is 5, 4, 3, 2, and 1. But with all the values, you can get these are 7 options, and we found that this one actually produces the maximum one plus 1. 9 plus 3, 12, 12 plus 1. What is 40? This one has the maximum reward 40, and we get this one when actually M to 6 is equal to 1. What is this one? What is this one? Anybody? Since we get maximum reward, this maximum reward when actually 1 unit of resources is allocated. Consider this one is 2 and B3 5 as we have seen here is 12. So this 2 actually is coming when actually we are allocated 1 unit of resources here, and this actually. And finally, when we have in this case, when we have actually, if we focus here, when we have B3, when we have B2, now when we calculate B1, then actually, what should be the allocated resource here? We need to allocate all 6 resources here. But here we need to consider all possibilities. B2, 0 to 6. B3, 0 to 6. Why is so? Because when we consider here 0 to 6, that means in this step we are using 0, then we can use 0. If both are 0, then we must have to allocate 6 here. That's why in the first step, in the first activity, we will calculate for the total resources to be allocated. Right? And here, since this one, then following the text, 6 we have option. We can use 0 in the first activity, 1 in the first activity, 2, 3, 4, 5, and 6. And by this way, the maximum will be 18, and this will be there when this one is the 5 unit of resources allocated to estate 1, and 1 unit of resources allocated to estate 2, 1 unit becomes 2 reward, and this 5 unit becomes 16, so the total reward is 18. And now how this A1 and 6 is finding actually the ultimate result, where we have B6 maximum is 18, then we say this maximum is 18, where actually we have allocated 5 unit in x1, so x1 actually is equal to 5, and when we come here we find that d2 is equal to, where is this one? d2 is equal to 2, d2 is equal to 1, and then we go here, d2 1, what is the maximum value? The maximum value is 2, and this maximum value actually is coming when we are allocating 1 unit in resources 1. So this one is giving us 16, and x2 is equal to 1 is giving us 2. So the amount is 16. So by that we can find out the actually total reward that we can find by applying the equation. So you understand it or not? I think you already know this already. So once we have this one, then we move on to the Markov reward process. Markov reward process we already have discussed. What actually is here? A reward is given based on the transition. If the transition is from 1 to 1, then reward is R1. If the transition is from 1 to 2, then the reward is this one. Now, for this process, we want to calculate.
Coding question gets also easy question pareil.
Love.
This.
Oh. I thought it's love. Sorry. You have a class now? Someone loading here? Already?